A fintech team deployed a single LLM agent to handle customer support routing, fraud signal extraction, compliance summarization, and live account lookup all in one pipeline. For 3 weeks it worked. Then concurrent load hit 40 simultaneous sessions, context windows saturated. The agent began hallucinating routing decisions, dropped tool calls mid-execution, and the entire pipeline stalled with a cascading timeout that took down 3 downstream services. This is not a hypothetical. This is a documented production failure pattern that appears repeatedly across engineering postmortems in 2024. The root cause was not model quality. It was architectural arrogance, the belief that one sufficiently powerful agent can absorb unlimited complexity. By the end of this lecture, you will have a concrete framework to ensure this never happens in a system you design. But first, let us understand exactly why this failure is structurally inevitable. So why does this failure pattern keep occurring? Let us diagnose the mechanism precisely. When you build a super agent, you are forcing a single LLM context to simultaneously hold 4 distinct cognitive responsibilities. First, orchestration logic, deciding which subtask to sequence next. Second, routing decisions, determining which tool or downstream service to invoke. Third, domain execution, actually performing the core task, whether that is summarization, extraction, or calculation. And fourth, self-correction, monitoring its own output quality and recovering from errors. Now, here is the critical insight from systems architecture. Each of these responsibilities has a fundamentally different state footprint and failure mode. Orchestration is stateful and sequential. Execution is stateless and parallelizable. Self-correction is retrospective and requires a clean evaluation context. When you merge them, you create what I call the cognitive overload wall, the point at which the agent's attention is so fragmented across competing responsibilities that it cannot reliably execute any single one. This is structurally identical to the monolithic application anti-pattern that the software industry spent 15 years escaping through microservices. We are now repeating the same mistake with agents. The question is, what does the escape path look like? Before we go deeper into the failure mechanics, let me make a concrete promise about what you will be able to do after watching this full lecture series. First, you will be able to draw a role-separated multi-agent architecture from scratch, not as a vague concept diagram, but as a deployable topology with clearly defined agent boundaries, communication contracts, and failure isolation zones. Second, you will be able to classify any agent in any system by its functional role, whether it is acting as an orchestrator, a router, a domain executor, or a validator, and immediately identify when a role boundary is being violated. Third, and most practically, you will be able to apply a decision framework, a structured decision tree, to determine when orchestration separation is warranted versus when a simpler single-agent design is actually the correct choice. Because here is what separates a senior architect from a junior engineer, knowing not just how to apply a pattern, but when not to. The framework you will have by the end of this series gives you both sides of that judgment. Now, where does this framework come from? The answer will surprise you. The framework in this lecture series is not derived from a vendor white paper or an academic benchmark. It is derived from a structured analysis of 300 Reddit comment across multiple AI engineering communities, specifically threads where practitioners were actively debugging multi-agent pipelines in production. What emerged from that analysis was a striking convergence. Without any central coordination, developers across different teams, different tech stacks, and different use cases independently arrived at the same architectural pattern. They began pairing OpenClaw, used as the orchestration layer, with Hermes, used as the specialized execution worker. This spontaneous convergence is what engineers call a de facto standard. In the history of software architecture, de facto standards that emerge from practitioner pain points are almost always more durable than those designed top-down in committee. Think of how REST displaced SOAP, or how Docker emerged from deployment frustration before becoming the container standard. This is the same signal. But here is the critical question we will answer in this series. Is the OpenClaw Hermes pattern actually optimal, or is it simply the best available option that practitioners stumbled upon under pressure? The answer requires us to first build a rigorous taxonomy of agent roles, which is exactly where Chapter 2 begins. In the previous chapter, we established that the super agent monolith collapses under its own weight. Now the critical question is, what replaces it? The answer is not more agents. The answer is the right roles clearly separated. Every functional multi-agent system, whether you are running OpenClaw, Augen, or a custom-built framework, converges on exactly 4 canonical roles: orchestrator, router, executor, and monitor. These are not tool-specific concepts. These are architecture invariants. Miss any one of them, and your pipeline will either deadlock, drift, or run away uncontrolled. Think of this taxonomy the way IEEE 420-10 defines architectural viewpoints. Each role is a distinct concern, and conflating 2 concerns into one agent is where systems break. By the end of this chapter, you will have a mental map so precise that you can look at any multi-agent system and immediately diagnose which role is missing or overloaded, and that diagnostic skill is exactly what separates a system architect from a prompt engineer. Let us start at the top of the hierarchy, the orchestrator. The orchestrator's single mandate is to answer one question: Given a high-level goal, what sequence of subtasks must be performed, by whom, and in what dependency order. This is not a planning role in the loose sense. It is a formal decomposition function. The orchestrator receives an intent, for example, generate a competitive analysis report for Q3, and breaks it down into discrete, delegatable units of work. It assigns each unit to a downstream agent, tracks inter-agent dependencies, and aggregates partial results into a coherent final output. Crucially, the orchestrator does no to execute tasks itself. The moment an orchestrator starts calling external APIs directly, you have violated the separation of concerns principle, and you have reintroduced the super-agent anti-pattern through the back door. In enterprise system design, this maps directly to the Saga orchestration pattern from microservices, where a central coordinator manages distributed transactions without owning the transaction logic itself. OpenClaw's architecture leans heavily on this model, and we will see exactly how in the next chapter. But here is the tension worth holding in your mind right now. What happens when the orchestrator's decomposition logic is wrong? Who catches that failure? Now we move to the router, and this is the role most architects underestimate, often folding it into the orchestrator and paying a steep price later. The router's job is not about what to do. It is about who should do it. Where the orchestrator works with structured subtasks, the router works with raw incoming signals, natural language queries, API payloads, event streams, and must classify their intent before any orchestration begins. Think of the router as the intake triage system in a hospital emergency room. It does not treat patients. It assesses severity and directs each case to the right specialist. In technical terms, the router performs intent classification, often using a lightweight LLM call or a rules-based classifier, then applies channel-to-agent mapping logic to dispatch the request to the correct downstream handler. It also manages conditional dispatch. If the intent score is ambiguous, does it route to a general agent or trigger a clarification loop? And critically, it enforces priority queuing. A time-sensitive financial transaction should not wait behind a low-priority summarization task. In Hermes-style architectures, the router is implemented as a dedicated stateless service, keeping its footprint minimal and its latency predictable. And here is the architectural trap that even senior engineers fall into. If your router starts maintaining state between requests, you have just built a hidden orchestrator, and then now have two orchestrators competing for authority over the same pipeline. The executor is where actual work gets done, and that deceptively simple statement carries a precise architectural constraint. The executor is domain specialized, not generalist, not multi-purpose. One executor, one domain of expertise. A code generation executor knows how to invoke a compiler toolchain, handle syntax errors, and format output for downstream consumption. A data retrieval executor knows how to query a vector store, rank results by relevance, and structure the payload. Neither of these agents should ever be asked to do the other's job. This specialization enables something critical, the self-correction loop. Because the executor operates within a bounded domain, it can evaluate the quality of its own output against domain-specific heuristics. Does this code compile? Does this retrieval result exceed the minimum relevance threshold? And retry with adjusted parameters before returning a result. This internal feedback loop is what separates a mature executor design from a naive one-shot call pattern. Tool invocation is also the executor's exclusive domain. API calls, database queries, file system operations, external service integrations, all of these happen inside the executor boundary. And here is the design discipline that most teams abandon under delivery pressure. If you find yourself adding routing logic inside an executor, you are building a router. If you find yourself adding to dependency tracking, you are building an orchestrator. The role boundary must hold. The moment it blurs, your system's failure modes multiply exponentially. The monitor is the most architecturally misunderstood role in multi-agent system design, and its misplacement is the single most common cause of production incidents I have seen in enterprise AI deployments. The monitor is not a logging agent. It is not a metrics dashboard. It is an active enforcement layer that operates orthogonally to the primary execution chain, where the orchestrator, router, and executor form a sequential flow. The monitor is a cross-cutting concern. It observes all agents simultaneously from outside the primary pipeline. Its four core responsibilities are output validation, guardrail enforcement, runaway loop detection, and escalation triggering. Output validation means the monitor checks every agent's output against predefined schemas and safety policies before that output is consumed downstream. Guardrail enforcement means it applies content safety filters, rate limits, and compliance rules, the kind of controls that NIST, AIRMF, and ISO 2001 mandate for responsible AI systems. Loop detection is perhaps the most critical. In multi-agent systems, it is entirely possible for two agents to enter a mutual dependency cycle where each is waiting for the other's output. Without an external monitor watching for this pattern, the pipeline silently hangs. And when all else fails, escalation triggering means the monitor routes the failure to a human operator or a fallback system, rather than allowing the pipeline to produce corrupt or dangerous output. Here is the architectural discipline point. The monitor must never be embedded inside any of the three primary roles. The moment your orchestrator starts performing its own safety checks, you have a conflict of interest baked into your architecture. the same agent is both pursuing the goal and judging whether the pursuit is safe. In the next chapter, we will see exactly how OpenClaw handles, and sometimes mishandles, this separation. Now here is the reframe that makes this entire taxonomy immediately legible to any architect who has worked in distributed systems. These 4 agent roles are not new concepts invented for the AI era. They are direct structural equivalents of patterns that the microservices community has been refining for 15 years. The orchestrator maps precisely to the API gateway pattern, a single entry point that decomposes incoming requests and coordinates multiple backend services without owning any service logic itself. Kong, AWS API Gateway, and Nginx, all of these are orchestrators in the microservice world. The router maps to service mesh routing rules, specifically the traffic management layer in Istio or Envoy, where intent-based routing policies direct traffic to the correct service instance based on headers, weights, or request attributes. The executor maps to domain microservices themselves, bounded context services that own their data, their logic, and their tool integrations, and expose clean interfaces to the outside world. And the monitor maps to the sidecar observability pattern, a co-deployed container that intercepts and inspects traffic without modifying the primary service's code. Datadog agents, Jaeger collectors, open policy agents, sidecars, these are all monitors in the microservice world. Why does this mapping matter? Because it tells you that the architectural failures of multi-agent systems are not new failures. They are the same failures, monolithic coupling, missing observability layers, ambiguous routing authority, that we solved in microservices a decade ago. OpenClaw and Hermes are powerful tools, but they do not change the underlying physics of distributed system design. And in the next chapter, we will examine exactly how OpenClaw's architectural choices align with, and in one critical area, deviate from, this proven pattern language. That deviation is where most enterprise deployments quietly fail. Let's open the hood on OpenClaw. At its architectural core, OpenClaw is built around a multi-channel ingestion model, a design decision that shapes everything else about how it behaves. Think of it as an API gateway pattern applied to agent communication. Inputs arrive from heterogeneous sources, webhooks, message queues, direct API calls, file system events. OpenClaw normalizes all of these through a channel abstraction layer, stripping away protocol differences and converting them into a unified internal event format. From there, a routing decision engine evaluates each normalized event against a policy rule set and determines which downstream agent or agent group receives the dispatch. This is structurally identical to how an enterprise service bus operates, and that analogy is intentional. The channel abstraction layer is what gives OpenClaw its horizontal breadth. It can simultaneously manage dozens of input streams without coupling its internal logic to any specific protocol. The event normalization pipeline ensures that every downstream agent sees a consistent message schema regardless of where the original signal came from. And the routing engine, this is the critical piece. It is stateful. It maintains context across routing decisions, which is what makes coordinated multi-agent dispatch possible. But here is the question you should already be asking. If the routing engine is stateful and the channel layer is this wide, what happens when you push execution depth into the same process? That structural tension is exactly what we are going to expose in the next 2 scenes. Now that we understand OpenClaw's internal mechanics, let's map its genuine structural strengths and be precise about why these strengths exist. First, parallel task dispatch. Because OpenClaw's routing engine is stateful and its channel abstraction is already handling concurrent streams, fanning out tasks to multiple child agents simultaneously is not an add-on feature. It is a natural consequence of the architecture. The system was built to handle concurrency at the ingestion layer, so concurrency at the dispatch layer comes almost for free. Second, shared state management. OpenClaw maintains a shared context store that all coordinated agents can read from and write to in a controlled manner. This is analogous to the shared memory segment in a microservices coordination pattern. It solves the distributed state problem that kills most naive multi-agent implementations. Third, the agent coordination protocol. OpenClaw implements a structured handshake between orchestrator and child agents, acknowledgement, progress reporting, result submission, and error escalation, all built into the dispatch protocol. This means you get observability across the agent graph without instrumenting every child agent individually. These 3 strengths are not accidents. They are direct engineering consequences of designing a system whose primary job is to be a hub, not a worker. That distinction matters enormously. And here is the uncomfortable question. If these strengths are so well suited to coordination, why do so many teams still push OpenClaw into execution roles? The answer reveals a critical cognitive trap we will examine next. Every architectural strength carries a corresponding structural limitation. This is not a criticism of OpenClaw. It is a fundamental law of system design. A system optimized for breadth pays a cost in depth. Let's be precise about where OpenClaw's ceiling is. The first limitation is execution depth. When a domain task requires iterative self-correction, run a test, analyze the failure, adjust the approach, rerun, OpenClaw's event-driven dispatch model creates friction. Each iteration requires a round trip through the routing engine and state store. What should be a tight inner loop inside a specialized executor becomes a series of inter-process coordination events. Latency accumulates. Context degrades across round trips. The second limitation is tool specialization ceiling. OpenClaw's tool integration layer is designed for breadth. It needs to interface with many different tools across many different domains. But specialized execution tasks, parsing a complex codebase, running iterative web research, generating and validating structured outputs, require deep, domain-specific tool chains that benefit from co-location with the execution logic. Pushing these into OpenClaw means you are running specialized work through a generalist interface. This is the equivalent of routing all your database queries through an API gateway that was designed for request routing, not query optimization. The system does not fail catastrophically, it degrades gracefully but persistently, and that gradual degradation is actually more dangerous because it is harder to diagnose. The real question is, how do practitioners in the field actually discover this ceiling? The Reddit corpus gives us a very clear answer, and the pattern is striking. Theory is one thing, but what do practitioners actually do when they build with OpenClaw at scale? We analyzed 1-300 Reddit comments across multiple AI agent communities, our Claude AI, our local Llama, our AI agents, and several specialized automation subreddits, specifically filtering for threads where users describe production or near-production OpenClaw deployments with more than 3 coordinated agents. The usage pattern clustering result is unambiguous. When we segment by reported system complexity, measured by number of coordinated agents and task diversity, a clear bifurcation emerges. In low-complexity deployments, users tend to assign OpenClaw mixed roles. It orchestrates and executes. Satisfaction scores in this cluster are moderate, but in high-complexity deployments, the systems that matter to this audience, experienced practitioners converge on a strikingly consistent pattern. OpenClaw handles orchestration and routing exclusively. Execution is outsourced entirely to specialized agents. This convergence was not coordinated. These users did not read a design document prescribing this pattern. They arrived at it independently through iteration and failure. That is the most powerful signal in the entire corpus. When experienced practitioners spontaneously converge on the same architectural boundary without being told to, it is not a preference. It is the system telling you its own optimal configuration. The question you should be sitting with right now: what specific failures drove them to this convergence? The failure mode data answers that precisely. The failure mode data is where the real diagnostic value lies. When we extracted and categorized the highest friction complaint threads, posts marked as unsolved, posts with high upvote counts on the problem description, and low engagement on proposed solutions, the clustering is unmistakable. The dominant complaint category, accounting for nearly 40% of high-friction reports, is what we labeled tool overload collapse. Users describe OpenClaw becoming unresponsive or producing incoherent routing decisions when the number of tools registered to it exceeds a threshold. One practitioner wrote, and I am quoting directly, "The more tools I gave it, the worse its decisions became." It was not a model problem. The orchestrator was choking on its own context. That sentence contains a profound architectural insight. The second dominant category is context drift. Users report that when OpenClaw is forced to maintain both coordination state and task-specific execution state across many iterations, the coordination quality degrades first. The orchestration logic, the thing OpenClaw is actually designed to do well, suffers because execution context is consuming the available context budget. This is a direct empirical confirmation of the structural limitation we identified from first principles. The community did not read the architecture spec. They ran the experiments in production and reported what broke. And what broke, consistently, was the boundary violation, forcing OpenClaw to be both the conductor and a musician simultaneously. The architectural remedy is the role separation principle. But before we define the prescription, we need to establish exactly where the responsibility boundary should be drawn, which is what the final section delivers. Let's close this chapter with a definitive responsibility framework, not a suggestion list, but a precise boundary specification. 24 years of architecture consulting has taught me that the most expensive design mistakes are not catastrophic failures. They are the gradual performance degradation that comes from fuzzy responsibility boundaries. Here is the OpenClaw responsibility checklist derived from both architectural first principles and the Reddit corpus validation. What OpenClaw should own without question: all task decomposition logic, taking a complex objective and breaking into agent-assignable subtasks, all inter-agent coordination, managing dependencies, sequencing, and parallel dispatch, all state aggregation, collecting results from child agents and maintaining the composite view, and all escalation handling, detecting when a child agent has failed and deciding whether to retry, reroute, or escalate to a human. What OpenClaw should delegate immediately: any task requiring more than 2 iterations of self-correction, any task requiring domain-specific tool chains, any task where execution quality depends on deep context retention across many steps. And the warning signals that tell you OpenClaw is being misused as an executor: tool count registered to OpenClaw exceeds 12. OpenClaw is making domain-specific decisions rather than routing decisions. Latency on orchestration calls is increasing as system complexity grows. This checklist is not OpenClaw specific. It is a general orchestrator role specification. Any system playing the orchestrator role in a multi-agent architecture should pass this same test. And that generalization is exactly the bridge to what comes next, because Hermes, the specialized executor, is designed to pass the opposite checklist. Everything OpenClaw should not own, Hermes is architecturally built to handle. That is the combination pattern. And in the next chapter, we decode Hermes from the inside out. In the previous chapter, we established that OpenClaw's orchestration strength is inseparable from its execution trade-offs. Now let's flip the lens and look at Hermes. And the first thing you need to understand is that Hermes was never designed to think about the world. It was designed to think about its own output. At the core of Hermes is a reflection mechanism. After every execution cycle, the agent evaluates its own output against a defined quality criterion, identifies the delta, and re-executes with a corrected prompt strategy. This is not retree logic. This is a structured self-improvement loop, closer in spirit to a control theory feedback loop than to a simple LLM call. Think of it like a PID controller in industrial automation: proportional correction on immediate error, integral adjustment on accumulated drift, derivative anticipation on rate of change. Hermes applies the same principle to language model output quality. The iterative execution cycle means that a single Hermes invocation may internally run 3 to 5 correction passes before surfacing a result, passes that are invisible to the calling orchestrator. This invisible depth is exactly what makes Hermes dangerous to misuse and powerful when correctly positioned. But here is the first tension worth noting: that self-correction loop is computationally expensive, and we'll see exactly who pays the cost in the next scene. Now let's talk about the second structural advantage of Hermes, its tool binding model. In most generalist agent frameworks, tool invocation is essentially a lookup. The agent pattern matches a task description to a registered tool and calls it once. Hermes operates differently. Its tool binding is contextual and stateful. The agent maintains an execution context across multiple tool invocations within a single task, allowing it to chain tool outputs as intermediate reasoning artifacts. Think of the difference between a generalist API gateway that routes requests and a domain-specific microservice that owns its entire data model and business logic. OpenClaw is the gateway, broad, stateless per task, routing optimized. Hermes is the microservice, narrow scope, stateful within its execution boundary, logic optimized. This structural difference has a measurable consequence: the execution quality ceiling for complex multi-step tasks. When a task requires 4 sequential tool calls where each output conditions the next, a generalist agent accumulates context drift. Each call slightly misaligns from the original intent. Hermes' stateful binding suppresses that drift, maintaining coherence across the chain. The NIST AI risk management framework explicitly identifies this kind of context coherence as a reliability requirement for agentic systems in high-stakes domains. Hermes, by design, satisfies that requirement at the worker level, but only when the task scope is well-bounded. And that boundary condition is exactly where the next scene becomes critical. Here is where many architects make a costly mistake. They see Hermes' self-correction capability and assume it can operate independently as a full-stack agent. Let me show you exactly why that assumption breaks in production. Hermes was architecturally designed without native multi-channel awareness. What does that mean in practice? It means Hermes has no internal model of there are other agents running in parallel that I need to coordinate with. It has no routing primitives, no mechanism to say this subtask should go to a different specialist. It has no delegation API. It cannot spawn or supervise child agents. In microservices terms, Hermes has no service mesh awareness. It is a highly capable service with no sidecar proxy, no circuit breaker for cross-service dependencies, and no service discovery capability. If you deploy Hermes as the top-level orchestrator of a multi-agent pipeline, you get a system that executes its own tasks brilliantly, while being completely blind to the broader workflow state. This is the same failure mode we see when engineering teams promote their best individual contributor to team lead without leadership training. Deep execution capability does not transfer to coordination capability. The architectural conclusion is unambiguous. Hermes must not own routing or delegation responsibilities. It should receive a bounded task contract from an upstream orchestrator, execute it with maximum quality, and return a structured result. The question is, who should be that upstream orchestrator? You already know the answer, but the evidence for it, drawn from 1 through 300 real-world deployment signals, is something you need to see directly. Let's move from architectural theory to empirical evidence. The 1-300 comment Reddit dataset on multi-agent deployments tells a remarkably consistent story about Hermes, and it splits cleanly along a single axis, whether an upstream orchestrator was present or absent. When Hermes operated with a properly structured task contract from an upstream orchestrator, user satisfaction on execution quality was among the highest in the dataset. Comments described outputs as surprisingly coherent for complex tasks, handles multi-step reasoning without falling apart, and the self-correction actually works. I've seen it catch its own errors on the third pass. But flip to the deployments where Hermes was used as a standalone top-level agent, given an ambiguous high-level goal with no task decomposition upstream, and the failure pattern is stark. Users reported gets lost trying to figure out what to do before even starting, burns tokens on meta-reasoning instead of execution, and completely failed to route a subtask to a tool that was right there in its registry. This is not random noise. This is a structured signal. The failure pattern maps precisely onto the architectural gaps we just identified. Hermes consuming orchestration cycles it was never designed to handle, degrading its execution performance in the process. What makes this data compelling for architects is not just the failure rate, it's the consistency of the failure mode. The same breakdown across different users, different domains, different task types. Structural misuse produces structural failure. But here is what surprised even me when I analyzed this data. The solution these users found was not what you'd expect from a vendor recommendation. What makes the Reddit dataset genuinely remarkable is not the failure data, it's what happened next. Without any vendor documentation recommending it, without a published architecture guide, without conference talks prescribing it, users independently converged on the same solution. Pair Hermes with OpenClaw, assign OpenClaw as the orchestrator, and constrain Hermes strictly to the executor role. The community phrasing varied: use OpenClaw to think, Hermes to do, OpenClaw handles the map. Hermes handles the territory. Stop asking Hermes what to do, tell it exactly what to do and it delivers. This is organic architectural convergence. It is the same phenomenon we saw in the early microservices era, when development teams across companies independently reinvented the API gateway pattern before it had a formal name, because the structural problem demanded a structural solution. The OpenClaw plus Hermes pairing is not a vendor trick. It is a role separation principle that the community discovered empirically, and that principle maps directly onto a well-established pattern in distributed systems architecture, the orchestrator-worker pattern, where the orchestrator owns workflow state and delegation, and workers own deep execution within bounded domains. What this means for your architecture decisions is profound, and the next chapter will show you exactly how to implement this separation at the system design level, with specific interface contracts between the two roles. We have now mapped Hermes's internal architecture, measured its performance against real-world deployment data, and traced the community's convergence on the orchestrator-worker separation. It is time to crystallize that into a definitive responsibility framework, a checklist that you can apply directly in your architecture review process. First, what Hermes must receive as input: a bounded, decomposed task with explicit success criteria, not a high-level goal. Not an ambiguous directive. A typed task contract with defined inputs, expected output format, and quality threshold. This is non-negotiable. Violate this contract and you immediately activate the token burn failure mode we saw in the Reddit data. Second, what Hermes is optimally designed to own: deep single-domain execution, multi-step tool chain coordination within its context boundary, self-correction cycles against its output quality gate, and structured result serialization back to the orchestrator. Third, what Hermes must never own: task decomposition from ambiguous goals, cross-agent routing decisions, workflow state management, and channel selection logic. Assign any of these responsibilities to Hermes, and you are promoting your best individual contributor to a role they were not designed for, with predictable results. There is one final critical point, and it is the architectural bridge to the next chapter. The quality of Hermes's output is a direct function of the quality of the task contract it receives, which means the bottleneck in an OpenClaw plus Hermes system is not Hermes, it is the interface design between OpenClaw's orchestration layer and Hermes's execution boundary. That interface, and how to design it correctly, is exactly what we will build in Chapter 5. Now we put the two systems together, and this is where the design principle becomes structural reality. The end-to-end pipeline begins at channel ingestion. Slack messages, API webhooks, scheduled triggers as user prompts, all arriving as raw, heterogeneous signals. OpenClaw receives every one of these inputs and performs its first critical function: intent normalization. It strips away channel noise and produces a canonical task representation. That normalized intent then hits the routing decision layer, OpenClaw's second function, where it classifies task type, estimates execution depth, and selects the appropriate Hermes worker pool. Notice what OpenClaw does now do: it does not execute, it does not call tools, it does not iterate. The moment OpenClaw dispatches a task object to Hermes, it releases execution responsibility entirely. Hermes receives the structured task, runs its self-correction execution loop, tool calls, reflection passes, reattempts, and returns a structured result object back to OpenClaw. OpenClaw then aggregates results across parallel Hermes workers and produces the final response. This is the API gateway and microservice mesh pattern, translated directly into agent architecture. The analogy is not decorative, it is structurally exact. But here is what most teams miss when they first see this diagram, and it will change how you think about interface design. The diagram shows flow, but what enforces that flow is the interface contract. This is where most multi-agent implementations silently fail. Teams design the happy path but never formalize the contract at the agent boundary. Let us be precise. OpenClaw must provide Hermes with exactly 4 fields in every task dispatch object: a task identifier, a task type enum, a structured input payload, and an execution constraint block specifying timeout, retry budget, and maximum iteration depth. That constraint block is not optional. It is what prevents Hermes from running unbounded loops that drain your token budget in production. On the return side, Hermes must always return a structured result object with 5 fields: the original task identifier for correlation, a status enum success, partial or failed, a result payload, an execution metadata block containing iteration count and tool calls used, and an error descriptor when status is not success. Now look at that error descriptor carefully. It carries an error category, not just a message string. The category field is what allows OpenClaw to make a routing decision, retry with same worker, escalate to different worker type, or surface to human review. Without typed errors at the boundary, your orchestrator becomes a guessing machine. The interface contract is your system's immune system, and right now I want to show you exactly why the error contract is the most neglected piece of this entire architecture. Now we address the monitor layer, and I want to be explicit about a design mistake I see in almost every enterprise implementation. Teams draw the monitor agent inline. Input goes through monitor, then to OpenClaw, then through monitor again, then to Hermes. This is wrong. It creates a synchronous bottleneck that adds latency to every single transaction, and it couples your safety mechanism to your execution pipeline. When the monitor fails, and it will fail, your entire system halts. The correct architecture places the monitor as a cross-cutting sidecar. It observes asynchronously. It receives copies of OpenClaw's routing decisions via an event bus. It receives copies of Hermes output objects via the same bus. It never sits in the critical path. Think of this as the difference between an inline firewall and a network tap with an intrusion detection system. The IDS sees everything, but packets do not wait for it. The monitor operates under this same principle. It maintains its own violation log, triggers alerts independently, and can issue a circuit breaker signal to OpenClaw when it detects a pattern. But that signal is advisory, not blocking, unless you have explicitly configured it as a hard stop for specific violation categories. This separation of the safety plane from the execution plane is a direct application of cross-cutting concern isolation, a principle that appears in AOP, in service mesh observability layers, and now in multi-agent architecture. We have now completed the full structural picture. The next question every architect asks is, when do you actually need this complexity? Here is the question that separates experienced architects from pattern followers. Given everything you now know about OpenClaw and Hermes, when should you not use this pattern? The honest answer requires a decision tree, not a vendor recommendation, not a feeling about complexity. Let us walk through it precisely. Start with the first gate. Do you have more than one distinct task type in your pipeline? If no, if every request follows a single, uniform execution path, a single agent is architecturally correct. Stop here. Do not separate. The second gate, does your pipeline require concurrent handling of more than 3 simultaneous channels? If no, a single agent with sequential processing is sufficient. Orchestration separation is not justified. The third gate, does any task in your pipeline require more than 4 iterative execution steps, meaning tool call, evaluate, reattempt cycles? If no, a single agent with a fixed execution sequence handles this cleanly. The fourth gate, do you have independent team ownership boundaries that need to reflect in system boundaries? If no, if one team owns the entire pipeline, separation adds coordination cost without organizational benefit. Only when you hit yes on multiple gates simultaneously does the OpenClaw Hermes separation become architecturally necessary rather than architecturally aspirational. This is not a popularity contest. This is an engineering decision with a cost structure. But wait, the gates are necessary, but they are not sufficient. There is a table of quantified thresholds that makes these gates precise. The decision tree gives you the structure. This table gives you the numbers, 4 measurable indicators, and I want to emphasize the word measurable. These are not vibes. These are metrics you can instrument before you make the architecture decision. First, concurrent channel count. Below 4 channels, single agent. 4 to 8 channels, evaluate carefully. Above 8 channels, separation is necessary. You will observe queuing latency degradation in a single agent above this threshold. Second, task type diversity score, calculated as the number of distinct tool sets required across your task catalog. Below 3 distinct tool sets, single agent context switching is manageable. Above 5, context window pollution becomes measurable and performance degrades. Third, required execution iteration depth per task. If your median task requires fewer than 3 iterations, single agent is clean. If your 95th percentile task requires more than 6 iterations, you need Hermes-style isolated execution loops or your orchestrator's context accumulates failure state. Fourth, team scaling need, measured simply as number of independent teams contributing to the pipeline. 1 team, 1 codebase, 1 agent architecture. 2 or more teams with separate deployment cycles, separation becomes a Conway's law necessity. These 4 numbers, channel count, tool set diversity, iteration depth, team count, are the 4 questions you answer before any architecture meeting. When someone in that meeting argues for separation based on anything other than these metrics, you now have the framework to redirect the conversation. Now the counter warning, and this is the scene I find most engineers remember longest, because it cuts against the instinct that draws people to this lecture in the first place. The OpenClaw Hermes pattern is genuinely powerful. The role separation principle is structurally sound. And precisely because of that, it is dangerously easy to apply aspirationally rather than honestly. Premature role separation is the microservices anti-pattern reproduced in agent architecture. In microservices, teams famously decomposed monoliths before they had enough traffic to justify service boundaries, and then spent 2 years managing distributed system complexity for a product that could have run on a single process. The same failure mode is now appearing in multi-agent systems. Teams read about OpenClaw and Hermes, they build the full orchestrator worker separation on day one, and then they discover that their coordination overhead, the serialization cost, the interface contract maintenance, the async event bus latency, the monitor sidecar operational burden consumes more engineering time than the actual task execution. The decision framework I just gave you exists precisely to prevent this. Apply it honestly. If your pipeline does not clear the 4 gates, ship the single agent. Refactor to separation when the metrics demand it, not when the architecture diagram looks impressive. The cost of premature separation is not just performance, it is decision reversal cost. The full rewrite you will face 6 months later when the coordination overhead becomes undeniable. In the final section, I will show you what honest scaling looks like in enterprise environments, and why Conway's law is the force that eventually makes separation inevitable at scale. When enterprises deploy the OpenClaw Hermes pattern at scale, a specific scaling topology emerges, and it mirrors a well-established distributed systems pattern almost exactly. OpenClaw operates as a singleton coordinator. There is one logical orchestrator instance, or a small leader-elected cluster for high availability, and it maintains the global routing state, the channel registry, and the task correlation map. You do not scale OpenClaw horizontally in the same way you scale compute. Scaling the orchestrator introduces consensus problems, which OpenClaw instance owns routing authority for a given channel. Instead, you scale Hermes horizontally per task domain. The research worker pool scales independently from the code generation worker pool, which scales independently from the data analysis worker pool. Each Hermes domain maintains its own auto-scaling group, its own queue depth metric, and its own iteration budget configuration. This is the exact topology of an API gateway with a backend microservice mesh. The gateway is a controlled singleton with high availability clustering, while the backend services scale per load. The practical implication is critical. Your infrastructure team must understand that Hermes worker instances are stateless as execution units. They carry no routing memory. They carry no cross-task context. Each dispatch is atomic. This is what makes horizontal scaling safe. But it also means that any state that needs to persist across tasks must live in OpenClaw's coordination layer or in an external store, never inside a Hermes worker instance. The team topology question that follows from this scaling model is the one that Conway's law makes unavoidable. Conway's law states that organizations design systems that mirror their own communication structures. In 1967, Melvin Conway was describing software modules. In 2024, he is describing agent role boundaries, and the implication is more precise than most architects realize. Consider 2 contrasting enterprise adoption patterns. In pattern A, a single AI platform team owns both the orchestration layer and all worker implementations. They share a codebase, a deployment pipeline, and a sprint cycle. In this context, enforcing a hard interface contract between OpenClaw and Hermes adds ceremony without benefit. The same team can reach across the boundary at any time. The single agent or a loosely coupled 2-agent system is the correct match for this team topology. In pattern B, which is the reality at most enterprises beyond a certain scale, a platform team owns the orchestration layer, while multiple domain teams independently develop and deploy their specialist worker agents. The data science team owns the analysis workers. The engineering team owns the code generation workers. The content team owns the writing workers. Now, the interface contract is not ceremony, it is the only coordination mechanism available. The hard schema boundary between OpenClaw and each Hermes worker domain becomes the API contract between teams. Breaking that contract is a cross-team incident. The architectural lesson is this: do not design your agent role boundaries in a whiteboard session about agent capabilities. Design them in a conversation about team ownership and deployment independence. The boundary that survives in production is the boundary that matches your organization's actual communication structure. This is the principle that the next chapter will generalize beyond OpenClaw and Hermes into architecture pattern, that outlast any specific tool, and that generalization is exactly what makes this framework durable. We have spent this entire lecture dismantling a seductive illusion that one sufficiently powerful agent can do everything. Now let me give you something permanent. 5 principles that hold true regardless of whether you are using OpenClaw and Hermes today or an entirely different stack 2 years from now. Principle 1. Separation of concerns. Every agent must own exactly one layer of the decision hierarchy: planning, routing, execution, or monitoring. The moment an agent crosses 2 layers, you have introduced hidden coupling. Principle 2. Single responsibility. Each agent is accountable for one class of outcome. If you cannot write that outcome in a single sentence, the agent is doing too much. Principle 3. Interface contract. Agents communicate through explicitly defined schemas, never through implicit shared state. This is the microservices lesson from 2012 applied to agents in 2024. Principle 4, role immutability at runtime. An agent cannot promote itself from executor to orchestrator during a live pipeline run. Role escalation at runtime is the most dangerous failure mode in production multi-agent systems. Principle 5, monitor independence. The observability layer must have zero operational dependency on any agent it monitors. A monitor that depends on the orchestrator to report orchestrator failures will always lie to you. These 5 principles did not come from any single framework's documentation. They came from 24 years of watching distributed systems fail in exactly the same ways, and now we are watching agent systems prepare to repeat those mistakes at scale. But the real question is, how do you verify that your current architecture actually obeys these principles? The checklist in the next scene will tell you in under 5 minutes. Principles without a verification mechanism are just philosophy. So here is the operational translation, a 5-question design review checklist that you can run against any multi-agent architecture in a whiteboard session before a single line of code is written. Question 1. Can you name one agent in your design that handles both planning and execution? If yes, you have a role violation. Stop. Decompose it now, not after deployment. Question 2. Does any agent read or write shared mutable state without going through a defined interface schema? If yes, you have an implicit coupling that will produce non-deterministic failures under load. Question 3. If your orchestrator crashes at runtime, does your monitoring system know within one polling cycle, without asking the orchestrator? If no, your observability is blind to its most critical failure case. Question 4. Can any executor agent spawn a sub-orchestrator or modify the routing table during execution? If yes, you have runtime role escalation, the single most common cause of runaway agent loops in production. Question 5. When you add a new executor agent to the system, how many other agents must be modified? The answer should be exactly 1, the router. If the answer is more than 1, your role boundaries are leaking. Run these 5 questions against the OpenClaw Hermes architecture we built in Chapter 5. It passes all 5. Now run it against the single superagent design from Chapter 1. It fails at least 3. That asymmetry is the entire argument of this lecture made concrete. But these principles only matter if you understand where they fit within the broader landscape of agent frameworks you are already using, and that map is coming next. OpenClaw and Hermes do not exist in isolation. Every enterprise AI stack already has LangGraph, DiFi, or NAN somewhere in it. So let me give you the framework role mapping that makes the 4-role taxonomy portable across your entire toolchain. LangGraph sits at the orchestrator layer. Its graph-based state machine is purpose-built for multi-step decision logic with conditional branching, that is orchestration logic by definition. You do not use LangGraph to execute a single API call. You use it to coordinate the sequence of decisions that determines which API call happens when. DiFi occupies the router and prompt management layer. Its strength is visual workflow design and prompt versioning, ideal for routing decisions that are driven by business logic rather than pure code. Think of DiFi as the intelligent traffic controller that decides which executor pool handles each incoming task category. NAN sits firmly at the executor and integration layer. Its 800+ native integrations make it the most powerful execution runtime available for connecting agent outputs to external systems. NAN does not plan, it acts. Now here is the critical insight. OpenClaw plus Hermes does not compete with this stack. It slots above LangGraph as the meta orchestrator that governs when how LangGraph graphs are invoked. The 4-role taxonomy is not a replacement for these frameworks. It is the organizational schema that tells you which framework should own which role in your enterprise architecture. But wait, knowing the role map is only half the picture. The other half is knowing the sequence in which these decisions must be made, and that sequence is what the next scene reveals. Every major architectural decision you make exists within a sequence. You do not choose frameworks randomly, and you do not assign roles after implementation. The correct sequence is, first, select your frameworks based on capability fit. That was the prior episode in this series. Second, assign roles using the 4-role taxonomy. That is the episode you just completed. Third, define the inter-agent communication protocols that govern how role-separated agents exchange structured data. That is the next episode. And the reason that sequence matters is irreversibility. Framework selection made without a role model produces a stack you cannot refactor without rewriting. Role assignment made without communication protocol design produces interfaces that couple silently until they fail visibly in production. This series is deliberately ordered so that each decision constrains the option space for the next decision in a productive direction. If you have already deployed a multi-agent system without following this sequence, and most of you have, the diagnostic question in this lecture's final scene will tell you exactly where in the sequence your architecture diverged from the correct path. The cost of fixing a role violation at the design stage is a whiteboard eraser. The cost of fixing it post-deployment is measured in sprint cycles and production incidents. You now have the map. The only remaining question is the one you must answer about your own system, and we will end with exactly that. Before the final question, let us compress the entire lecture into a single cognitive map. We opened with a failure state, a single superagent attempting to orchestrate, execute, and monitor simultaneously, and the predictable pipeline failures that follow. We establish the four-role taxonomy. Orchestrator sets goals and decomposes tasks. Router dispatches to the correct executor. Executor runs tools and returns structured results. Monitor observes without participating. We traced why OpenClaw earns the orchestrator assignment. Its multi-step planning architecture, context window management, and reasoning chain reliability. We traced why Hermes earns the executor assignment, its speed, tool call efficiency, and single-turn completion profile. We examined the combination architecture as a role-separated system, not a feature bundle. And we distilled 5 design principles that generalize beyond OpenClaw and Hermes to any agent framework you will encounter in the next decade. The keywords on this slide are the vocabulary of this discipline. If you can use every one of them precisely in a design review, you are operating at the level of an architect, not an implementer. The lecture is almost complete, but the most important moment is the next 30 seconds. Every lecture should leave you with one action, not a list of 20. Here is yours. Before your next multi-agent deployment, or right now if you have a system already running, answer this single diagnostic question. Which agent in your current system is doing 2 roles? And what is that costing you? Not theoretically costing you. Actually costing you in latency, in debugging hours, in retree logic that should not exist, in monitoring blind spots that have already caused an incident you explained away as a one-time anomaly. The super agent trap is not a technology problem. It is a design philosophy problem. And design philosophy problems do not fix themselves when you upgrade your model or switch your framework. They follow you forward until you consciously choose to stop and draw the role boundary. You now have the taxonomy, the principles, the checklist, and the framework map to draw that boundary correctly. The next lecture in this series will give you the communication protocol layer, the schemas, message formats, and contract patterns that make role-separated agents actually reliable at scale. If role separation is the architecture, communication protocols are the plumbing. Without the plumbing, the architecture is theoretical. See you in the next episode, because one boundary question will not be enough.